Welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue talking about ElasticNet. And in this implementation video, we'll look at mostly how to implement ElasticNet, ElasticNetCV, MultiTaskElasticNet, and MultiTaskElasticNetCV. And to begin with, we'll also try to attempt to see the grouping effect using ElasticNet. So let's get into Jupyter Notebook and start coding. Here I've imported these libraries: NumPy, datasets, linear model, matrix, train, test, split, and matplotlib. And these these are the versions I'm using. Now, before we begin, I want to make a note about L1 ratio that we'll be using in this one. So L there is a L1 ratio, and we can set this ratio for ElasticNet. So the L1 ratio of that is uh, equal to 0 means it's strictly going to L2 penalty. And if it's L1 ratio, L1 underscore ratio of uh, 0, and if it's L1 ratio of 1, then it's L1 penalty. So we'll look at the effects of this. So this will be similar to ridge, and this would be similar to lasso. And the range, so the L1 ratio would lie in the range between 0 less than or equal to L1 ratio, L1 ratio, 1 ratio, and less than equal to 1. So that's the range in which we can tune the value of the L1 ratio. So with that in mind, let's first import the data set. So let's get the data. And for data, we'll use the same Boston data set that we used in the previous video. So data is equal to data sets dot load underscore Boston. And here we have x underscore train, y underscore train, sorry, y x underscore test, then y underscore train, y underscore test is equal to train underscore test underscore split. And here we can specify data dot target. And if you remember from previous video, we can look at what's inside the data by typing this. So if we print this, we can see that this particular data set has 506 rows. It has 13 features. Are these, and it has one categorical feature. Sorry, one target, which is this one, median value. So we will be using all of those. Now to see the effect of grouping, so let's see, e- ElasticNet and grouping effect. So for this, we'll update this data that we created by adding additional columns, because we need more features than more features than rows. So let's create another data set. Xg underscore train, yg underscore train is equal to x underscore train. So we are taking the rows from the x train that we have just created, the n rows, and we'll specify the value of n rows here. So let's say initially we'll specify n rows is equal to say 100, and we can change that as we go through the code if needed. And then we have a y train that goes again from 0 to n rows, and here that's for the train. We'll copy this and we'll create the same thing for test. So xg underscore test, and then yg underscore test. Again, this will take the data from the x test, and this will take from the y test. So that is the n rows. So that is what we'll be using for grouping. Now Here we can go ahead and add collinear features or columns. So we'll create them. What we'll do is we'll take the first column and add it a couple of times. So how many times? Let's start with 50. So Q will create a new data set Q, a new array Q, and what that will have is initially it will have just one column from this data set X train, and all rows and just a 0th index column. And then for this one we'll multiply it by 2, and after this we'll change the axis. So if you look at the Q dot shape, it would be this. Now if we add new axis, so all rows, and here np dot new axis, so now we have that one. So now we have that as a column, and to this we'll do a concatenate. So q train is equal to uh, we'll concatenate to this. So we'll use a for loop. So for I in range n, what we'll do is we'll create a bunch of columns using the queue that we have created above. So queue, and it just has one column, so we just have that, and to this we'll multiply by I by say 100.0, and this is just to change the values in the column queue as we are adding them. So we have some new points in there, but they will be correlated because it's the same value divided by constant in the new column. So here again we are new axis. So this will create a uh, list of columns, and then what we can do is we can concatenate all of them. So concatenate, and here we can specify the axis is equal to 1, so it will concatenate along the columns axis 1, and finally we'll convert this to an array np dot array. And now if you look at the q underscore train dot shape, we have 100 rows and 50 columns. So we just created 50 columns from that one column from the xg train. Now what we need is we need to create the exact same thing for the test set as well. So let's do that. So here instead of p, I'm going to change that to q because we are going to use the test instead of train. So test, and this will be again p instead of q. Now once we have this, we can go ahead and check the shape of p, and sorry, this should be p underscore test, and we can check that shape. It should be 100 p underscore test. Okay, it's 100 by 50, so that is good. Now final step is we need to add these to the xg test that we xg train and test that we created right here. So this is add back to the main. So xg underscore train is equal to np dot concatenate, and here we specify the list. So xg train, that's the first original one, and then to that we are going to add these extra columns, and we need to specify the axis is equal to 1 so that it's stacked side by side to the columns. And then the second one is xg test, and this will add the columns right to the test on the column side of the column. So finally we can, just to confirm that everything is what we were expecting, we are going to type out print out the shapes of this. So xg train dot shape, that's the first one, and then we'll also print out on the new line xg underscore test dot shape, and here we can type xg underscore test dot shape. So let's see, there is an error, q underscore test. Oh, that's right, because this would be p. And so we do have 113 columns in the xg train, but we should have the same number of columns in xg test. So let's check if there's we are missing something. So p underscore test dot shape is good. Okay, now we are good. So actually it should be 63 because we had original 13 features, and to that we are adding 50 features more, so we have 63. So this is good. Next, let's now try some experiments to see how the changing the LR ratio. So we have LR ratio and alpha value. So LR ratio will first set it to 0.75, and alpha value will set it to 0.15. And when we run, and with that in place, we can now create the fit and train. So we'll create a variable regg, and g is for grouping, and that's the variable linear underscore model dot ElasticNet. And within this we need to specify L1 ratio. And so this is, I've been calling LR earlier, so the same L1 ratio, and this is LR, which we specified above, and then alpha is equal to alpha, which also we specified above, and we'll set the random underscore state is equal to 0, and normalize is equal to true. Once we have this, you can go ahead and fit this. So regg dot fit xg underscore train yg underscore train, because this is a special data set where we have introduced 50 collinear features, uh, with the intention to see how ElasticNet versus Lasso works on this. So then we calculate, get the coefficients. So coefficient is regg dot coef, and we can print these out. So let's do that. Print see coefficients, and these coefficients we can print them on new line, of course, and coefg. And after this we'll also count this. So print the zeroed coefficients. And when we, but the issue with this particular count is that if it's a float with many zeros after the decimal, and it's not actually zero, it won't count it as a zero. So we'll see how to work around that. EFG. Okay, so LR is not defined, that's because, okay, the COEFG. Okay, so we have the coefficients working. Now we'll go ahead and also do the prediction, just so we can check how the MSE or the mean squared error changes. So we have regg dot predict, and this would be on the test set. So xg underscore test, and we'll calculate the mean squared error MSE, and this is for groups. So I put a G there. Matrix dot mean underscore squared underscore error, and here we have YG underscore test and YG underscore pred. So we can now go ahead and print the MSE, and this would be MSEG. Now as you can see, with the L1 ratio of 0.75, just to remember that when we are talking about lasso, we need to be closer to 1, so to see the effect of lasso. Here we are at 0.75, and alpha is 0.15. So just to remember, what alpha does is, higher the value of alpha, the more stringent the constraints are, so lower would be the values of the coefficients. And so here we are at 0.5, so we have much relaxed value, alpha value in here. Now I'll copy all of this and paste it here, and this will change it to lasso. And for lasso we do not have L1 ratio, so I'll remove that. And furthermore, this will change it to lasso. So that's a different variable, lasso. And same thing here, we'll change this to lasso. And going to copy this so we don't have to type it. Okay, and again copy this here. Now this would be y pred, and this is lasso. Again, this is y pred, and this is lasso. Okay, and this would again be lasso. So with all these metrics, we should be able to see. Okay, now as you can see, with lasso, for the same alpha value, all these coefficients are zeroed. In addition to these coefficients are also zeroed. Whereas in this case, if we where is the print here, if we round this, so round to maybe 4 decimal places, and we need to suppress the scientific notation. So np dot set underscore print options, and here we can specify suppress is equal to true, so that will suppress the notation. Now as you can see, the output is non-zero, and this is all zeroed out. So that's the case when we have uh, alpha learning ratio of 0.75. Now if we change that, if uh, we look at the alpha learning ratio, and if we keep the same learning ratio and change this alpha value to 0.5 and now run this, we can see that uh, in this case we did zero all the newly added correlated features, and we zeroed the original feature that was associated with those correlated features. So uh, in this particular case it did seem to work, uh, although in case of lasso the same effect is seen. So I tried couple more examples to see the effect where the elastic net either keeps or drops the collinear features, whereas the lasso does pick one or the other. However, these were the examples that I could come up with. You could try changing the values for alpha and learning ratio to see if you get different results. So for example, if you change this to 0.3, now uh, the elastic net, it doesn't drop any of the correlated features, it keeps all of them, it keeps the original one also. Now when we look at this one, this still drops everything. So maybe that's the flexibility in the approaches. However, if you look here, due to collinearity, the MSE for this particular elastic net has now increased to 60, whereas it's only 44 for the lasso. Moving on, now let's look at another comparison between elastic net and lasso. You've already seen one, so this could be a repetition, but let's see the example. New set, we'll use the same data set. Now let's try how we can bring ElasticNet closer to Lasso. So for this, first try the Elastic, and here we'll use reg is equal to linear and model dot, and we'll specify the L1 ratio as 1, alpha value as 5, random state, random underscore state. Now fit it reg dot fit x and train y underscore train. Finally, the coefficient. COEF is reg dot COEF underscore. So that will print, and here we can backslash. Next, let's also get the predicted values. So get the MAC values reg dot predict x test, and from this we can calculate the MAC equal to matrix dot mean squared underscore error, and here we have y underscore test and y underscore y and spread. Finally, we can go ahead and P and MAC. So those are the coefficients and values. Now go ahead and use the lasso. So for lasso, change this part to L. Not need the L1 ratio from there. So that, and just to make this different, add a 0 in front of the OEF, and when we run this, we get the values coefficient for lasso as well. Now if we subtract COF minus F0, so we see that they are all 0. So all these coefficients from the ElasticNet method, where we set the L1 ratio to 1, are same as that we get for lasso when we have the alpha value as point. So that kind of supports what we have discussed previously, that changing the row value to 1 zeroes out the L2 bridge term. Similar to this, now let's look at how Elastic can approach ridge. So ElasticNet and approach ridge. So for this, we use the same method, slight diff. So I'm going to copy code for ElasticNet. And one change is that if you remember, for ridge regression, the objective function, we did not have the 1 divided by 2 n samples. We are not dividing by twice the number of samples. However, in the ElasticNet objective function, we are. So here for the value of alpha, would have to update it. We are dividing it by number of samples. So x underscore train dot shape 0. So that gives us the number of samples. That will be the alpha. And for the L1 ratio, we set it to 0. And for alpha, that's the alpha we are going to use. On this, those are the values for coefficient. And this error is because set alpha value converging object for a iteration. So we wouldn't worry about that right now. We just, these values are same as. So for ridge, and here we need to use the alpha value of 1, match what we have above. Ridge, everything else is same, and let's match CF minus, and so by setting the L1 ratio to 0 and having the alpha value here divided by the number of samples, is gives us the same output as with the ridge when the alpha value is. The reason this also confirms the intuition that we had discussed before, that when we uh, set the value of row in the objective function to 0, it zeroes out the L1 norm term, and what we are left with is the L2 norm, which is the ridge, and that's exactly what we have. Elastic ElasticNetCV. So for this, we'll first try ElasticNet and then try ElasticNet. So we have something here with ElasticNet, and for ElasticNet again we have reg underscore linear underscore model dot ElasticNet, and we have L1 ratio. We'll set the L1 ratio to 0.5 and alpha to 0.1. Random underscore state is equal to 0, and then we have reg dot fit x underscore train y underscore train, and finally we do the prediction. Y underscore pred is equal to reg dot predict, and here we have x underscore test. So let's go ahead and print the MSE. So MSE is equal to, and here we have matrix dot mean underscore squared underscore error, and we the y test and use the y pred. So y underscore test and y underscore pred. So that's the MSE we have. Now for ElasticNetCV, we'll use the same code. Copy that, paste it here. So this would be CV, this would be CV, and we can specify a range of L1 ratios and alphas. So we'll add those in a minute. And here we have ypred CV, reg CV, and then we have this ypred CV as well. So for the L1 ratios, we can specify, say, 0.001, and then 0.001, 0.01, then point 1, and maybe 0.5, 0.75, and let's go to 1. And after this, I'm going to use the same values for alpha as well. Okay, so these are the L1 ratios and alphas. So it has to be alpha with S, alphas. And when we run this, we get a MSE of 20.60. So this is higher than what we have for the MSE for ElasticNet by itself. So maybe this needs further fine tuning. Maybe value of 0.4 here could help, or so so when fine tuning, you can specify a lot more values in here. So you can get the best possible combination of the L1 ratio and the value for alpha. So maybe delete this because those are too small, and it's still 0.6. So in this case, I was hoping the ElasticNet CV will get a much better result, but in this case, it's not. Uh, so for sake of the video, I think you got the idea how to use ElasticNet CV. Now moving on, let's look at another method, which is MultiTaskElasticNet. MultiTaskElasticNet. And for this, we are going to uh, create output uh, output y matrix, because so far what we have is just one value as output, which is just a one y column. If we look at the y underscore train dot shape, it's just one column, but in multitask we need multiple output columns to check, and for that we'll add some values. So let's add random dot seed is equal to this is 0, and within this we'll use the y train. So y is equal to y underscore train, and this is np dot new axis. So what that does is it will have that 1 in front of it, as you can see. Now to this we'll concatenate a bunch of same values multiplied by some random number. So ym underscore train, so that will be our new output y that we'll use for fitting, and np dot concatenate, and within a list, and here we need to specify axis. So let's go ahead and do that. Axis is equal to 1, Now here we'll specify the very first one is y. Of course we need y, and to that y we'll append y into np.random number, and that is of the length y, and this will again change the axes of this. So let's, maybe after multiplication we can just add np dot new axis, and similar to this, copy that and add this here. So instead of rand n, we'll use random integer, and let's say numbers from 0 to 20, uh, and these mean numbers, and those will add, uh, multiply the y with that, and then concatenate all of those. So now if you look at the ym underscore train dot, m is for multitask, so dot shape, here we get a value of 3. So now we have 3 columns in the output, as against just one that we had before. So that's good. Next, let's use this same again, and we'll do the repeat the same process for test. So we'll use t y underscore test test, and then ym again is for test, and these values then can stay the same because we are using the y test value right here. And finally, we can print ym underscore train dot shape, ym underscore train dot shape, and then we have y, on the new line we have ym underscore test dot shape, and let's add another one, ym underscore test dot shape. So as you can see, we have successfully added 3 columns in the output. So now it's time to use the multitask ElasticNet and see what we get. So multitask ElasticNet ME will initialize a variable ME for multi-elastic, and then linear underscore model dot multitask ElasticNet, and here we are going to specify L1 ratio is equal to 0.01 and alpha is equal to 0.3, and then you have me dot fit, and this would be on the x train, and ym underscore train, the one that we just created. And finally we're going to predict, so yme underscore pred is equal to me dot predict, and here we have x underscore test, and then again we need the MSE, so we'll calculate that. And now the MSE is going to be different for each of the columns, so we'll use a for loop to do that. So for I in the range y underscore me underscore pred shape, so we are going to, we could have just simply typed 3 in there, but I used that to get the shape, and then using the second index from the shape. Yeah, matrix dot mean underscore squared underscore error, and this will be using the ym underscore test, and this would be the ith column because we are in the for loop now, and then the predicted value will be y underscore me underscore pred. Again, this would be the ith column that will match, get the metric. And finally it's time to print it. So print multitask ElasticNet MSE, and this is going to MSE ME. All right, so that was a silly mistake. I didn't type the shape there. So here is what we have. These are the MSEs for each of the regression outputs. So each output is a task, and we have 20, 578, and 1975. The MSE is increasing. Now why don't we compare this with Lasso multitask that we have tried previously? So multitask Lasso, and for this, let's type it out. So me, or why don't we copy it? Paste it here. So this is multitask Lasso, and this does not need the L1 ratio. So we delete that. This stays the same. Rest everything stays the same. I'll just change this name, multitask Lasso, and when we run this time we get a MAC that's slightly lower, at least for the first and the second output. For the third output, the MS is lower in case of the elastic. But here, the point was to show that these are very powerful methods. Elastic, if you have multiple outputs, say for example, you have data for uh, crop cultivation in a farm, and you have tried different types of fertilizers, different types of insecticides, or different types of seeds, different amount of water, sunlight, etc. And you want to check the effect of that on not only the yield of a particular crop, but also maybe the uh, quality, so taste of that, or maybe the color of that. And if those all can be trained on the same set of features or features, then ElasticNet could give you that flexibility to perform the regression analysis to get multiple outputs in one go. And finally, if you were wondering, is there a CV built in with the multitask? And the answer is yes. So this is unbelievable. So this is amazing. MultiTask ElasticNet CV. So let's try this. So why don't we copy this? I'm going to copy all of this. So everything stays the same. All we need to do is change add the letter CV there. I won't change the variable names this time. And here we can specify a list of, again, alpha and L1 ratios. So I'm going to copy those and paste them here. So we have now a set of values for alphas, set of values for L1 ratios, and using that we can use the multitask ElasticNet CV. And here we can also specify a random state, random underscore state is equal to 0, and we have the ym that is needed, x test, and then we are taking the test with ym as well. Okay, so this should be fine. We just need the CV in front. Now when we run this, as you can see with the multitask, we we do get a higher CV for the first column, which is the same output as we had before, uh, but that can be fine-tuned. And to so this is also the same as what we had. This is a little different. So the point is, with different parameters you have, these values can be fine-tuned further to get a model that is optimal and gives the lowest MSC. But one thing to always remember in cross validation is that uh, you don't want to overdo cross validation, because if your uh, even if your cross validation score is great, it does not always mean that that model is going to perform the best on unseen data. That may not be the case. It is possible that due to uh, over cross validation effort, the model could have started overfitting the validation data set. So that's also a possibility to keep in mind. That was it for this video. I hope in this and previous videos you got an intuition about what is ElasticNet and how the objective function changes by the value of row or the value of L1 ratio, and how it is related to the lasso and ridge. Additionally, we also looked at different coding implementations. We looked at the grouping effect, although it was not as convincing, or you get an idea to uh, kind of anticipate what could be happening, as well as we tried to compare the results for simple ElasticNet, ElasticNetCV, MultiTaskElasticNet, and MultiTaskElasticNetCV with each other, as well as with some of the lasso methods associated with the same type of methods that ElasticNet has. If you have any questions, comments, or suggestions, please let me in the comment section below. I hope to see you all in the next video. Please like, share, and subscribe. Thank you.